Hello, folks. Hopefully, I'm coming through this time. I think last time it may have started, but I had to reboot my program, so sorry to anyone who joined me for that last one. And hopefully, this time we will work a little better. Let me load open my chat here and make sure I can actually get it working from my end here. I am going here. I do need to change one thing here while I chat. So let me make myself big while we do a little introduction. And now that we're actually going and working here, I will reintroduce what's going on today, which is on another rainy day in my area. We might not be able to visit the combo classroom today. And so we're going to have to look at some indoor fun mathematical patterns or stories or things. And one of the things we'll be looking at is modular tables of modular arithmetic, a super underrated way of looking at numbers. And to start, though, we're actually going to first, after I make sure the stream has its stuff how it should, we are going to first look at some good old what's called times tables. And some will say not good old, bad old times tables, because those are pretty hated by a lot of generations because they were force taught in a memorization based way. Like, let me pull up here an example of what I mean by a times table, often known as a multiplication table. Here's one where they highlighted the diagonal because those are notable. We'll see why in a moment. And if you try and tell kids you gotta memorize your 12 times 11s and make sure you keep that locked in your brain, the kid might not like it that much. Especially if you go past this and you think past this means 13 times 12 and all sorts of stuff, and then you gotta memorize 17 times 13. But that's not really what being a mathematician or a great thinker is. We can look for patterns in the times table that tell us much more beautiful and interesting things than caring about trying to copy what a calculator can do. You can rely on a calculator to tell you you're 17 times 13. Or maybe you should have a way of doing it in your head in a way that might take 10 or 15 seconds. That's fine. Maybe it's, if you ever need to know 17 times 13, it can take you 10 seconds to calculate it. But to know some inner patterns on a times table, that's stuff that can be beautiful and should be taught a lot more. And one of those simple underrated things is these highlighted diagonal ones. The numbers that lie on the diagonal are our square numbers. And those are probably taught in terms of, okay, well, when the number times itself hits the diagonal, which will only be when something was times itself to be in a diagonal spot, we get what's called a square number. Some number n times the same n squared. But what they don't always tell you is how if we count the appearances of each number on this chart, well, let's see how many times 3 appears. Only in 3 times 1 and 1 times 3. How about 11? That only appears on 1 times 11 and 11 times 1. How many times they appear isn't dependent on their size. It's dependent on if they're prime or not and how composite they are. A composite number will appear more than twice. 1 only appears once, and primes appear twice. And we're imagining the chart being infinitely big, so like 13 would appear twice in total on here. And we're imagining all the other appearances of some of these. So, for example, even though we can only see 2 15s on here, there would also be 15 times 1 and 1 times 15, giving it more than 2 appearances, making it not prime. And what they don't tell you also when you're first learning your times tables is if we count the appearances of most numbers, they come an even amount of times because this is symmetrical. 3 times 5 is the same as 5 times 3. And because of the symmetry, because A times B is the same as B times A, we get double appearances of anything not on the diagonal. And so anything not on the diagonal only comes in pairs and has an even number of appearances or factors. And really the amount of appearances is the amount of factors. And so the only ones that appear an odd amount of times are the ones that hit a diagonal. And meaning the only numbers with an odd amount of factors are square numbers. And one way of visualizing that is that square numbers would have to lie on this diagonal line to hit something times itself, and that anything that's not on the line comes in a pair. Ones that come on the line could have stuff in a pair as well, but they have something not in a pair, making them end up with an odd number of appearances. So if and only if you have an odd number of factors or odd number of appearances on this infinite chart, you're square. Now, there's even more interesting things we could try and find here. What happens if I look at numbers near the diagonal? Well, if I go up and diagonal from here, like to the diagonal away from the diagonal, from out of the inner diagonal, one away in a diagonal fashion, it's always one less. Look, 4 to 3, 9 to 8, 16 to 15, 25 to 24, 36 to 35. It's always one less. Why is that? Well, that's because if we look at n squared compared to n plus 1 times n minus 1, which is what's happening when we do that, well, n squared minus 1 can always be factorized. Like, let me type this. If we have, well, no, we have a whiteboard here for a reason. We can say that n squared minus 1. So, well, here's some patterns we noted. N squared has an appearance on the diagonal. These are going to come in handy when we look at our modular versions. So, n squared, the number, has an appearance on a diagonal, or on, like, main diagonal. Then we can note that n squared are only n. What I'm meaning here, the n's that can be expressed as n squared are the only n that have an odd number of appearances. So that meant odd number of factors. And then what we can note here is n squared minus 1. So this expression can always factorize into n plus 1 times n minus 1. But what does this mean in terms of our table? This means that the number on the diagonal will be 1 bigger than the number that lies on these squares. This is like the column n plus 1 times the row n minus 1, or vice versa, which is row and column, means this refers to an actual spot on the times table. So we could see that here, that like for 4 squared, so that's 16, 4 squared minus 1 could be written as 4 plus 1 times 4 minus 1, and that's where it lives, on the 4 plus 1 times the 4 minus 1. So they're always one off there. We can find other cool patterns too, with things that are near there. Lots of cool patterns. But we'll start with those, the n squared minus 1s. And let's also note that there are kind of 2 types of numbers that I like to think of as almost square numbers. One type that I like to think of as almost square numbers are numbers that are like this, because if you add n by n, the area would be n squared. So if you have something with an area of n squared minus 1, the area is right off from a square. However, the side lengths of that would be an n minus 1 and an n plus 1. So another arguably different way of saying I'm almost the square is if it's just like an n and an n plus 1. Also could be phrased as an n and an n minus 1. Because these, the sides are 2 off from each other. the sides are 1 off, but the area will be different there. The area is going to be n times n plus 1, or it could be times n minus 1, depending how we phrase that. And so those ones are the ones called pronic numbers randomly, that are also known as oblong numbers, that are when you multiply two integers together and get something. So like 3 times 4, or like 5 times 6. So as you go up this type of almost diagonal, the ones that are just touching the diagonal, so like right on the sides, those are these other fellas known as pronic numbers. So we'll keep an eye on those as well. So this is a big ol' normal times table, but this isn't the modular part. And looking at the comments, someone's wondering about, they're calling them Picasso periods, but they're called Pisano periods. Slightly different word first, but they are very interesting. Those relate to the Fibonacci sequence taken in different mods. So that might be a different day's topic. I haven't mentioned that in any streams or videos yet, that exact way of looking at the Fibonacci sequence. But when we introduce the modular tables today, the concept of those Pisano periods is basically the idea that we could take what we're going to learn about modular numbers and apply it to the type of sequences you'd have on the OEIS and see how they behave. And it turns out the Fibonacci sequence will be cyclical under different mods. So will things like triangular numbers. So certain tables on the OEIS, those integer sequences, may have loops when we do them in a certain mod. So now, this is a times table the old normal way. But when you look at the modular way, what happens is our times table gets cut off. It describes infinity in a finite amount. And the way they do that is they loop around like a clock. Now, if we were talking about clock math, that could mean a lot of stuff. We could mean, oh, a clock has 6 factorial minutes in 12 hours. And that's just because of the high divisibility. And so we could talk about highly composite numbers are sort of related to clock math. Could also mean, like I've shown, this homemade clock is about the unit circle. So the unit circle has some modular phenomena in it that are similar to this modular arithmetic, where if I take I squared, I get -1. I cubed goes there. I to the 4th power is there. I to the 5th power is I again. And so we sort of loop back around. I to a certain power, taking I to an integer, basically behaves as a mod 4 table. It has 4 states it flips between. So to make a mod table, one way of looking at it is, after I hit the biggest number, I loop back around to 0. The biggest number, which I name my mod after, actually becomes 0. And then the number after that is 1, and so on. And so it's like a clock, so a lot of people call it like a clock type of math. Now, one thing it has better than a clock is it starts at 0. Unlike stupid clocks in society, that those 12-hour clocks we use go from 1 to almost 13. And the 12 functions as a 0, so why not make a 0? So on modular tables, you actually get a 0. So like if I look at the mod 12 addition chart, this is like if we described clocks with 12 actually being 0, and I'll go to mod 12. Come on. Let's retry this page. Mod 12. So this is like if we said a clock had 0 instead of 12, and I wanted to add 2 hours. Where would I end up? Well, if I add 5 hours and 4 hours, I end up at 9. If I add 6 hours and then 7 hours, I end up at 1, because 13 hours on the clock sends you to 1. So if zeros are really what we're calling 12s, then we go forward. Someone asked how they work in negative numbers. I mean, we're assuming our mod will be a positive number here. But if we say we want to interpret a negative number, we go backwards. So -1 in this mod is 11. -2 in this mod is 10. It would be like going counterclockwise. So there are even mods where division is well defined, but it turns out your mod needs to be a prime number to have certain traits about division work. And so with normally we like our mod to be a really divisible number with how we do clocks and stuff, but it's kind of the opposite you'd want for some traits to work. So unfortunately, there are like half of the cool episodes I'm going to make about mods are like, check out how cool it is in these really divisible mods, and the other half are going to be a little different, like, check out how cool this other trait is in prime mods. And yes, 20 is a pronic number because it is 4 times 5. Now, pronic numbers, as I mentioned in a short, are the sum of the first n even numbers. So if I go 2 plus 4 plus 6, that gets me 12, which gets me, and then plus 8, that equals 4 times 5. So pronic numbers turn out to be the sum of the first n even numbers, just like square numbers are the sum of the first n odd numbers. Pretty wild, huh? Got some fun identities there. And to look at these modular tables, we actually need to start with getting a fundamental sense. I've explained this little bit in an episode on my main channel called Modular Multiplication Magic. So this next 5 minutes may be familiar to some of you. But I need to give this little intro for those who don't know, which is that if we're in mod 2, we can analyze this as remainders numbers have after division by 2, but we can also remember that that trait has a nickname in society. Numbers that have no remainder after being divided by 2 are called even, and numbers with one remainder after being divided by 2 are called odd. So this is telling us an odd and even table secretly. We're in addition land right here. So we see that any even plus an even's an even, any odd plus an odd is an even, and any one of one kind plus the other kind is an odd. That's always true. And now we can see in multiplication we get a different table that's really useful. Even times anything makes it even, and odd times odd still odd. So what about threevens? Now, threeven, one of our combo class quests that I'm on, is to get threeven in the dictionary. We'll be starting a petition at some point in grade -2. But what it really hinges on, because dictionaries aren't really looking for petitions, is for articles to be written containing that word. So to anybody who knows any journalists, please encourage them writing articles that contain the words combo class, demotro, and threeven. So, here in threeven land, we get threeven numbers are 0, and we get 2 types of throd, or non-threeven number. The post-threeven throds are what I call the ones congruent to 1, and congruent to means like what it equals in the mod. So congruent to 1 is our post-threeven throds, and congruent to 2 is our pre-threeven throds. And we can see our table. We get a addition table. Anytime you add a threeven with a threeven, you get a threeven. If you want other ways of getting a threeven or adding one of each different type of throd together, and you get these other tables. And we get a multiplication table here too that tells us what happens under that. Like a pre-threeven throd times a post-threeven throd will be post-threeven, but a post-threeven times a post-threeven will be pre-threeven. And now we're starting to get our first type of interesting thing to point out here, which is that we said the diagonal was important. We said that numbers on the diagonal are the only square numbers, that square numbers have to fall on the diagonal. Now we're not going to be looking at the odd number of appearances thing. Let's look at, because these tables have been restricted and limited in a different way. But it's still going to be true if you think about it, that any square number has to lie on the diagonal. Because, like, any number, any integer is a 0, 1, or a 2. And so any type of integer times itself is one of these diagonals. So the square numbers still have to be on the diagonal. And check it out. There are no 2's on the diagonal. There's only 0's and 1's on the diagonal. And that actually tells us something very interesting, which is that no square numbers are pre-threeven rods. All square numbers are either threeven or post-threeven rods. We can also rephrase that as no square numbers are 1 under a multiple of 3. They're all either the multiple of 3 or 1 over. Because the ones that are 2 over are the ones that are 1 under. And we can check and verify it and be like, okay, so these are our first square numbers. And it's like, what are they in mod 3? 1, 1, 0, 1, 1. Next one would be 0. And we actually are going to get a recurring pattern like this. 1, 1, 0, 1, 1. And I should have started with 0 as technically a square number, so that's technically threeven. So 0, 1, 1, 0, 1, 1. And so that's our diagonal. 0, 1, 1, 0, 1, 1. If we keep like going around the bend on the diagonal. So it's true that square numbers come in a pattern. Threeven, post-threeven, post-threeven, threeven, post-threeven, post-threeven. Never pre-threeven. Never the ones that are 2 more than a multiple of 3 or 1 less than a multiple of 3. So, what about other mods? Well, mod 2 was too small for that to help because 0 and 1 appeared. But what about mod 4? Look at this. Only 0's and 1's out of all these possibilities. Every square number is either 0 or 1 more than a multiple of 4. That is a good limiting factor if you were curious if a number is square, but you happened to know how close it was to the nearest multiple of 4. Square numbers can't be 2 or 3 more than a multiple of 4. They alternate between going multiple of 4, 1 more, multiple of 4, 1 more. So these diagonals are very important in number theory because they're, in a different mod, the only things square numbers can be. And as you go up, it seems kind of perplexing that they all hold true, that every square number is either 0 or 1 more than a multiple of 3, either 0 or 1 more than a multiple of 4, either 0, 1, or 4 more than a multiple of 5, either 0, 1, 3, or 4 more than a multiple of 6, and it keeps going. All of these hold true forever. Some of them are pretty limited, like 16 only has 0's, 1's, 4's, and 9's. Every square number is either 0, 1, 4, or 9 more than a multiple of 16. And some of these relate to clocks, so that's why I came up with my own analogies in my episode about this, where 12 tells us about 12-hour clocks. If you have a clock starting at noon, and you spin forward a number of hours, that same number amount of times, like 5 hours 5 times, or like 7 hours 7 times, or whatever, that's secretly making a square number in mod 12. So if you take a clock at noon and go any amount of hours that many times, you're gonna end up at either noon / midnight, 1, 4, or 9. So that's pretty wild. And in mod 24, you get your own patterns, which you can see in my episode on the main channel if you haven't later, called Modular Multiplication Magic, which goes over some of this stuff as some clock analogies. And we can make weekday analogies with mod 7. You know, cubes, it turns out, have a neater pattern in mod 7 than squares, but cubes aren't as visible on this chart. So these can tell us real cool things, and those diagonals that are very notable in number theory, which are the what square numbers can be in a given mod, are called quadratic residues. And these quadratic residues are super important. In fact, so I read a bunch of books about number theory, and here's a couple books about number theory that I was reading recently. Grab the ones I was going through on that topic. Don't have the other one I was reading a minute ago, but these are a few on number theory. And these books all are very excited about quadratic residues and all have a lot to say about it. It's a very deep, applicable concept and has a lot of fun stuff that you can use it for. But let's just look at a little table of some of them. They've got to have. Okay, here we go. So, they decided to put some red, meaning whether or not it's coprime. Coprimeness is another story that modular stuff can tell us. And in fact, we came back to modular clock analogies in one of my other videos on the main channel, which was about these spiky star shapes. And those related to coprimeness. So here they color-coded them, but you can ignore the color coding for now, and we can just note that some of these that are sparse, that don't have as many members, can tell us interesting things, like that every square number is one of these amounts more than a multiple of 24. And so those are pretty neat. Quadratic residues. Gotta like those. Now, those were our multiplication tables when we were in the mod. If we go to our addition tables, those are a lot simpler looking. We can see this wave of numbers fly by. And here's an interesting thing about the addition tables is, so I made it similar to a dice analogy in a whole different episode about dice, where if we say I'm rolling 2 6-sided dice, but pretend 0 says 6 here for all these. Pretend these zeros are 6s. And then let's say I roll 2 6-sided dice, take the sum, but subtract 6 if it's more than 6 to put it in the range of 1 through 6. Then I would end up with this chart, but with the zeros as 6s. And what's interesting is we get an equal odds of hitting all the numbers, because for all the ones that got cut, they reappear. It's like 1 1 1 1 1 1 2 2 2 2 2 2 3 3 3 3 3 3 4 4 4 4 4 4. So they all get an equal number of appearances. Same with any of these for addition. They all get an equal number of appearances here in the mod when we run it under addition. So a lot more predictable under addition than under multiplication. But it's still kind of fun to look at these. They still look pretty cool. I put that one in the thumbnail instead of the multiplication because while it's less interesting, it looked more visually engaging with that stripe. Now, with this stripe, we're going to have to go back to normal times tables to see something really cool. Now, this next one I haven't even mentioned in an episode, and it will definitely come up, because someday there will be an episode on the main channel about extreme times tables. We'll find a way to make times tables extreme. But what we got to note here is, where do our, under multiplication again, what if I try and see on a big mod where the multi-digit numbers hit? It's kind of confusing because the bigger multi-digit numbers became small again, so we can't really see that. But on a normal times table, let's look at times table big. And where's a big one? Okay, here's a pretty big one. So on this times table, it's very blurry. Work with it. So on this times table, the blurriness might actually help us visualize something. Do you notice if you just squinted your eyes, that some parts are darker than others and it comes in kind of a wave. This top corner looks lighter because it has less digits in it. And then when the 2-digit numbers hit, you kind of see like a thicker portion that comes in like in this wavy thing. Like, and then over that, we see the 3-digit numbers make a darker looking thing because they're thicker and more filled in with their digits. So we can sort of see this curve where the more amounts of digits hit. How can we visualize that? Well, we're saying that kind of like on a graph, if we flipped this, it would be flip the other orientation, but we would be saying we have an x times a y. When was it more than 10 gave me that line because it was double digit. When was it more than 100 gave me that line. Well, it's time to pull open our friend Desmos and see if we can look at that line. Because if I graph when is x times y greater than or equal to 10 versus when is x times y greater than or equal to 100, we get those shapes. They're just flipped on the axis because we're looking at it upward now instead of looking at it this axis way. So, see those curvy shapes? There they are. And we would see more of them, actually, if we saw a bigger times table. We would see it look a little thicker where the 1,000-digit numbers were written because they take more digits. So, that's an interesting pattern that times tables have that we'll look at. I'll try and find a way to animate that sometime. Although we kind of just animated it there, but we'll find a way to actually visualize this on a massive times table. So, to anyone who wants to animate me a massive times table, email me at the contact link. Because that probably won't be a grade -1 episode. That's why right now I was feeling okay doing a bunch of my current thoughts on all the modular times tables and stuff, knowing that I'll have a more polished, better version of this with more and more fun facts when we actually do a full episode about extreme times tables. Let's see. A lot of interesting thoughts. Someone's wondering what's my recommendation on learning this information. And first, someone's wondering if it's mod 100, if it'll only have the square numbers before it. No, it will include the square numbers before it as quadratic residues, but it could have other ones. We just got lucky on some of them that it was only the square numbers under it. So we just got lucky on like mod 16 or 24 there. Other ones will loop around to other spots. And thank you all who just left nice comments. Very nice. To whoever said they love me. I love you all very much too. Someone's wondering what functions with modulus look like, and they're very interesting. I don't think we can do them on here necessarily. Can we? Like, y equals x mod 3. I don't think they let us do that. Mod requires 2 arguments. Mod 1, 3. Nah, that's not doing modular arithmetic here, I don't think. I don't know. So, I don't know how we would program that in Desmos. But, that you can try and do functions under that. And someone was wondering where my recommendation to learn about this, and I would recommend reading a bunch of books about it, or reading online stuff to start. Like, not that it will be your end source you would quote in a research paper, but that Wikipedia article about quadratic residues probably has a lot of great stuff in it. I've read a lot of those Wikipedia articles and found them really engaging. And then if you want to really dive in and have a slightly more trustworthy source, you can get a trustworthy book. So this one's really great about number theory. really awesome. There's a bunch of other ones I'll recommend sometime when I have my full stack. Um, let's see. Yeah. Bunch of books here. We could look at my stacks of books in a minute if people want. It could be a fun game once in a while to pick a random number, like from my 100-sided die or something, and go to one of the random pages when you, which we could, I mean, like pick a number and go to that random page in a bunch of the books. So y equals mod, put the x in there, and then n is the mod, they say, maybe? Yeah, so I guess that does work. Maybe. So let's try, these are interesting. Yeah, so we could have fun with these ones at some point. Oh, look, it's like teeth chomping. Doesn't that look like teeth chomping? With a tongue in the middle? They always look like weird stuff. So, someone asked if 9 equals 0 when using base 10, but 9 wouldn't equal 0 in base 10. 10 is when you reset to 0 in mod 10, and that's why we don't have a symbol for 10. It got another digit, but basically the mods, they're not identical to counting in a base, but they're pretty identical to the last digit a number would have in a base. So if I was in base 12 and I multiply two numbers, these are possible last digits then, a symbol for 10 and a symbol for 11. Then if I multiply something with that last digit by something with that last digit, this is the last digit of my result. So it's basically it tells you about singular digits behaviors in a base. And bases are like stacks of this in a weird way. So tells you a ton about how a base would function. For example, the fact that 6's table is so neat is part of why 6 would be a good base to count in. So what if n is another function? Someone's wondering if that works. Let's see if that works. Yeah, maybe it does. That's cool looking. Look at that. Oh no, we don't even have an n anymore. That's trippy. What if we say it's less than or equal to that? This is trippy. The mod makes it have weird glitches like teeth in it, sort of. Oh no, I made them the same. Okay. Let's try one of our weird combos where we're like, sine of y is less than or equal to that. Okay, a lot of interesting stuff we could try here in the future. I'm liking where this is going with the mod idea. So, I didn't even realize this stream was going to verge into a Desmos stream, but we might have to come back to some Desmos today to try seeing if we could reinterpret some of our old equations in a modular way. Like, one of our classics, for example, was sine of x squared plus sine of y squared equals a. And is there a way we can put this in? mod of ooh, we got a lot of cool creatures. So the mod is good at separating different creatures. Oh no, N is up here. Yeah, I like the mod because we can make creatures out of this a lot easier. Um, these are fun. Ooh, whoa, that's trippy. These are wild. Okay. What about another classic? Over there we had sine of x times sine of y equals sine of x over y. And I don't know if that's going to fully work here, but we can try. This is wild. This is like a really weird type of chessboard. You start out with the board being like almost square, like that. This is how you start out your chess game, and then as you play, the board slowly shifts. Like, whoa, it shifted too fast. It slowly shifts like that and stuff. That would be a wild type of board game. Now the board's like this. Now the board's like that. Now the board's like that. This one's interesting. It looks like part of one we've seen before. Now it looks like the other part. So, that's pretty fun. Someone's wondering if this has a 3D mode. I don't think Desmos does. I think I might have to try out some other programs, like maybe this one called GeoGebra, to try and go further into graphing someday. I'm not really a tech guy, so maybe I'll have some tech whiz on my team helping me with this someday. For now, I like Desmos because if you just know a mild amount of how to make math equations properly formatted, then it does all the other stuff for you. It's pretty self-explanatory. So the trick is the creativity, is coming up with different ways to modify and vary these things as an experiment. So changing them is the creative part, to find different types. So, a lot of fun ones there. And someone's wondering the derivative of these. Interesting thought. And is this 4D chess? Maybe. I think it's the sequel to chess, Chess 2. Yeah, chess is a fun game, but it would be more fun if it went like this over time. Maybe not this one, maybe the ones where they inched around and changed. Look, it looks kind of like the YouTube play button. Got a lot of puzzle pieces. Alright, I guess it's time to try some of them as tangents in this type. Whoa, this one's weird. Whoa, this one's like hypnotizing me. This is like transmitting some weird secret subconscious info to us, some subliminal stuff from like some secret natural math force is communicating something here. Unfortunately, it's in a really weird base. It's in base 2i, so we're not interpreting it right. So, lots of cool ones there. We can come back to more of this, but let's just take one last peek at our modular tables. And I want to take a note on our modular tables to see how here we got 6, and it has some pretty tidy patterns. Like you got 0 going up, hopping up, jumping up. So it's like, you know, hop, hop, back, hop, hop, or like jump and back, and jump and back. Or the backwards hops, or backward steps. So 6 is really neat and organized and cool. And then we could go to like 12, and that one's pretty neat and organized. It looks a little more chaotic, but it has a nice pattern to it. And then we go to 10, and this is what the last digits of like are in our base. And this is not one of the best ones. Some of these patterns are really convoluted. It's a lot of weird ones. 06284, 06284. No wonder it's harder to memorize times tables when the last digits follow this pattern compared to the last digits following this pattern if we were in base 6. Everyone complains so much if they hear about base 6 about, oh, numbers would take slightly longer to write. Some of your 2-digit numbers would take 3 digits now to write. But it's like, come on, wouldn't you sacrifice having some of your numbers have one more digit for all the digits to have a better pattern? So, base 6 is a lot better for that reason. We also saw in the last stream that base 6 has better fractions. So those are just a few of the ones you got going for it. Base 6 also has a better proportion than 10 of coprime numbers less than it. And what that relates to is like my spiky star polygon one is like if I made an episode about this, but I'll draw the shapes again because they're fun. If we had like clocks that went 6 dots on them for 6 hours, if I hop 1 or 5 hours at a time, I touch all the dots in that shape, painted one direction or another. If I hop 2, I just paint out a triangle. If I hop, and yeah, if I said 6 does a smaller percent of whatever, what I meant to say there, I think I hopefully said right, was 6 has a smaller percent that are, coprime to it. And so coprime means they have no factors in common apart from 1, but it also means, with my dot analogy, that it's the shapes that hopping around clocks or certain dots on circles wouldn't touch, or the coprime ones touch all of them, and the non-coprime ones return to their same dot and paint out a shape that doesn't touch all the corners. If I hop 3 dots at a time on that 6-hour clock, I just end up with a line. If I hop 2 or 4, I do that. 1 or 5 is that. And anything congruent to one of those numbers paints that too. So here we can see that out of all my options for how much I could hop, only congruent to 1 or 5 touched every corner. And that means that in base 6, every multi-digit prime number would have to end up ending with those. I didn't make the connection right here. You can watch my episode about this if you want to see why that connection is there. It's on the main channel about spiky shapes. So as for why this implies this about primes, but it does imply that any multi-digit prime number is 1 or 5 more than a multiple of 6. Also meaning congruent to 1 or -1. That's the -1 in mod 6. So we could say any prime is 1 more or less than a multiple of 6. Any multi-digit prime, we're not counting 2 and 3. And really any prime 6 or larger. And so in base 10, primes can end in 4 things: 1, 3, 7, or 9. If you were looking for a prime, 40% of the last digits are possible for primes in base 10. In base 6, only a third of the digits would be possible. 2 out of the 6 possible congruent options. So it's a better proportion of less possibilities for your primes. Your primes are described in a more efficient way. And let's see. If base 6 is nice, how nice is base 12? Honestly, not better in my opinion. A lot of people like base 12 because they prefer the idea of adding symbols than deleting symbols. But come on, guys, the symbols we're deleting are kind of sucky. If we go in base 6, we only need 0, 1, 2, 3, 4, and 5 as our digit symbols. We're getting rid of 6 and 9 that are so freaking confusing of like, if you have a dice with one of these, you need to put a dot or a line under to be like, I'm not talking about the other one. They look like each other upside down. You get 7 that looks like a 1. You get 8 that looks like an infinity sideways. So these are the fine symbols to kick out. That's okay. Base 6 is getting rid of the confusing ones. Actually, no, these are confusing too. That looks like an O and that looks like an I or an L. But that's kind of, we can blame that on the letters, not the numbers. But base 12, people are more used to adding symbols than subtracting them, so they lean toward 12 than 6. But it's not as neat. Base 12, the fractions are slightly worse, for example, some of them. So base 6 is going to be honestly our most efficient, beautiful one. Also, 6 or 12 really work, though. 6 or 12 are really your best bases. Go 2, 6, 12, or your best bases are typically your superior highly composite numbers. So there are other ways you could count what would be the best base, but for many traits, these are the best bases. Now, 60 is a bit too high for us to use as how many symbols you want. 2 is a little short. It's a little small. 2 is not that efficient at writing data. In terms of takes a lot of characters. 2 is good for computers, but it seems pretty obvious when you analyze these that 60 is too much and 2 is too little for humans. So these are the way to go. 6 or 12, baby. 6 is even better, though. So thank you to everyone joining me and leaving your random comments. I love you all so much. And we will learn more and more about base 6. And there are some cultures that use base 60, yeah. Some of them, though, don't actually fully use 60 different digits characters, like symbols for it. Some of them are similar to a combo of a few. I think that some of the base 60s were sort of a combo of base 5 and base 12, which makes sense because check it out. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little joints on here. And so we can count in 12 that way by like saying which one you're on with the thumb. And then here you could either be counting that same way, or if you want to multiply it by 5, you can say how much you've multiplied it by here, if you want to just use fingers on one hand. So some use like 5 on one and 12s on the other and combining to be 60. So it's not always 60 different characters because that seems kind of inefficient, but they use versions of base 60 in some past cultures. And some wondered if computers should work in base 3. There are actually traits that base 3 maximizes. Having less digits does help computers, so 2 often is used. Base 3, however, does have a higher thing called the radix of the base, or the radix can be the not just related to the digits, but what is it called to maximize that? Radix economy, that's what it's called. The number in a base, to express it in the base, the number of digits it needs multiplied by how many symbols there are. So this is one way of calculating how efficient a base is. How many digits it takes to make a number multiplied by how many digits you have to memorize or whatever. Just one way of quantifying it. And it would be maximized by base E. But base E is not that efficient, so base 3 is better. Let's see. Yeah, here we go. E has the lowest, they say. And because of that, base 3 is the integer base with the lowest. So base 3 maximizes that a bit. And one that we'll go into in some episodes sometime is balanced ternary is something that some computers use. So more often than a computer using 0, 1, and 2, they weirdly use 0, 1 and a symbol that means -1. Kind of trippy, binary-esque, ternary-esque, and you could use it as a base where you're like, each of my spots, I am using powers of 3. It is a ternary system in that your positions are powers of 3, but instead of being able to have none, 1, or 2, you can have none, 1, or -1. And it actually works not the same way that base -2 or -3 would work when I did an episode about those, but reminiscent. We can, if we want to make the number 2, we do a -1 of the 3's plus 1 of the 1's place. If we want to make the number 4, we do -1 of the 9's place plus, what's that? Well, no, we do 1 of the 9's place plus -1. Wait, yeah, so I'm mixing this up. To make the number 2, we'd use 1 of the 3 and -1 of the 1's. To make the number, 4, we'd use 1 of the 9's and... to make the number 4, we'd use 1 and 1. And then to make the number 5, we'd have to use -1, 1, and 1. So it would be a little interesting and different. Whoever asked, I do have some private students I tutor. And a lot of that's actually music tutoring. I will do more music theory lessons at some point too. There will probably be at some point in grade -2 where I'll do a few music theories in a row. Have a little month dedicated to that. Will be kind of fun. Relates to math, but also is sort of its own separate fun skill you could have, understanding how things like piano and guitar use musical scales. And it will relate to clocks because there are 12 things in music, 12 different possible letters, and they move, letters counting the sharps and flats, 12 different keys, and they move in a circular fashion. And the fact that 5 and 12 are coprime, or that 7 and 12 are coprime, which imply each other, are related to why music works well. I haven't experimented much with just intonation, but I have, heard some things about it when I worked in a music shop before that were interesting. And lots of interesting thoughts there. Someone's saying we could use the English alphabet as base symbols, which would be, like base 26, but that we would want to cut a few. If we wanted to do that, we would probably want to just use 12 of them or 24 of them or something more divisible than 26. Because if we use 26 digits, then the fraction 1/3 is going to be hard to express. If we use 24, a lot of fractions will be easier to express. Let's see. to look at next, well, we could take a peek at how balanced ternary represents stuff because it's kind of fun. Here's an example of what I meant. To make 4, you could use +3 +1. To make 5, you have to use +9 -3 -1. It relates to problems we could make with weighing things, which we will do, where you can weigh. We'll do that in an episode later. There's fun puzzles about like how would you weigh so and some of them are solvable by balanced ternary. So that's a fun one. In fact, one of the shorts I made a while ago was a puzzle that secretly had some stuff to do with that. And what else are we going to take a peek at here? Well, balanced ternary is good, but I'm still leaning toward the superior highly composite bases. Those ones are really great. And in fact, I wonder if they mention that on here. That they are useful. Because another one that works well are these ones called primorials, have other traits that are helpful. Yeah, here's one. They say the first few superior highly composite numbers have also been often used as radices, which is the plural for like the base that you're using. So these are common highly composite recommendations. And this is a number we love here in combo class, the long hundred. The number as divisible as the regular 1,000. The long hundred of 120, so much better than the regular 100. A number that deserves so much more respect than the regular one. Oh yeah, the long 100. They have their own article just about that. Not even the same article they have for 120. Separate article for long 100. Here in our article for 120, we get a cool picture of the 120 cell, which is a 4D polytope. This was actually we didn't show this, but this was a member of a list in my episode about what shapes can exist in different dimensions, because this is one of the perfect polytopes, the convex perfect polytopes. And by perfect, I mean it's regular and has some of those traits. Regular, we define that in the episode and stuff. Look at all this stuff 120 can do. Look how glorious all of that is. We even see it in our bubbles. 3 soap films like to meet at that amount of angles if you're using degrees. So, interestingly, 120 is what they call untouchable. Even though it's so divisible, no number has it as the sum of its proper divisors. It's not the aliquot sum of any number. But its divisors add to twice itself. Oh no, its divisors including itself add to twice itself. I mean, add to 3 times itself, meaning its divisors not including itself would add to twice itself. And this is a multi-perfect number that we talked about in a different stream. And we'll come back to these multi-perfect numbers because we're going to talk about divisor sums more in a cool episode about what's known as friendly or solitary numbers. For example, 120 is friendly with all the other 3 perfect or tri-perfect numbers. But what else are friendly or not are interesting. So, that was most of the modular arithmetic stuff I wanted to take a peek at. Some of our fun tables and ways in which we can get clues. Another thing you could ponder on your own is, what does this mean about the numbers 1 to the diagonal or 1 to the side? Remember we said that pronic numbers are 1 to the side of the diagonal. And we said that numbers that are 1 less than the square in terms of total are that diagonal way. And we can see that. 1 goes to 0, 4 goes to 3, 3 goes to 2 and stuff. Let's go a little higher. Let's go to 12. We can see, 4 goes to 3, 9 goes to 8, 0 goes to 11, because that's 1 before 0 in this mod. And then we can also see the Pronic numbers, and we could actually make a similar thing. This struck me the other day for the first time. I haven't seen this written about much, but it made me wonder, and if any of you want to join me in my investigations of this, you can let me know if you find much research on this. But if quadratic residues get so much credit, I wondered, what about pronic residues? Could that be a thing? The residues you would get when you look at any pronic number in this mod. Like here we have 0, 2, 6, or 8 appear to be what all the pronic numbers are congruent to. So what pattern could you draw in terms of what pronic numbers can end up congruent to in a given mod? I think that would be interesting, and maybe it shares some secret traits with quadratic residues, so people can let me know if they want to join me in my quest of looking for any pronic residues. Now, since that was all I had planned for a moment, let me zoom into my camera and we'll stretch for a minute, maybe take a look at some of those books, or maybe get carried away with some chatting if anyone has any questions. You know, I have plenty of opinions and plenty of stories if anyone has anything to ask. Some of the stories and opinions have to wait till grade -2 or onward, but some of them are ready to unveil. So, I'm going to stretch for a moment and show you an example of one of my cool number theory books and what they might be saying about some of this stuff. But people can feel free to ask any questions for now before we end our stream. And we could also maybe see if it's non-stormy enough to go outside. Let me stick my head out the window and see if it feels super rainy or not. Alright, we're getting a mild drizzle. I don't think the computer is gonna like a trip outside. So, unfortunately, it's not a day for field trips. Alright. So we do have a few questions I'll answer here. Feel free to keep leaving any more if you want, but the rest of our stream may be mostly chatting centric. And how do I stay motivated to make my videos and stay on during my live streams? It's a good question. I actually sometimes wonder how I get so hooked on reading and studying math and talking about it. I kind of just roll with it because it's a strange like addiction I've developed to finding out facts about numbers. And so sometimes I just roll with the natural energy and I'm pleasantly surprised. But I've always been someone who kind of likes performing and likes talking a lot. Like as a kid, I would talk nonstop, and then I loved writing in notebooks and filling up notebooks with thoughts. When I'm not live streaming, I spend a lot of the day writing thoughts on paper or digital notebooks and just taking a lot of thoughts down. So I like conveying my thoughts to the world, and I'm a talker. My friends know I like to rant about things sometimes. And I can get just as carried away with ranting with my friends as on the streams. And sometimes in the day, I have a lot of trouble staying happy or motivated. I've had a hard year, and I deal with some mental issues like a lot of people do. So some days, you know, I have more so of some anxiety or depression or other things going that I actually, unfortunately, deal with. That you might not see as much because I'm able to tap into this really excited mode. And so sometimes I stream because I kind of know that when I'm kind of feeling like I'm performing and learning and chatting and stuff, it makes me tap into my best self, and I'm less likely to think about anxious or depressed things. When I'm talking to other people, it's a lot more likely sometimes that I'll like try and be my best self and feel natural with that. So I don't know, I guess I have a lot of strange natural energy, and I like to put myself on the spot, because when I get in the flow of my strange natural energy, I can enjoy the hour a lot. And I don't know, maybe there's other techniques I'll share over time when I make some more philosophical videos and stuff. But it's definitely not for everyone. The bit that stresses me out more, though, is the technical parts. I don't like having to worry about uploading videos and tagging stuff, and I'm not the biggest fan of editing stuff either, always. And a lot of stuff like that stresses me out more so. Sometimes even communications, just like I'll be late on communicating with people because I'm stressed to check my email that day. So that's stuff that I'm like less efficient on sometimes. But once I build more of a team and continue to have more various people who are helping me and I'm working with and hiring or just helping me or various things, then I'll be able to extra tap into the parts I enjoy, which are that I do have a weird, strange, natural energy to just want to talk to people and share a bunch of stuff with the world. And I think that I have a lot of stories to tell from my past and a lot of opinions and thoughts to share over time that I always feel like I'm still only touching at the tip of the iceberg of what I want to say, even at the end of a long stream. So I don't know. I hold my opinions to like a high standard sometimes, in that I'm like, oh, I'm capable of having some really brilliant opinions that inspire people. So I always try and, force myself to do as close to that as I can as part of my day. And it can be good to sort of ritualize things, to put yourself in movement, and working on a project can put you in a better mood than just stalling and stuff. And so when I sign up for a stream, I kind of know that I'll be like in it to win it for a few hours. And same with when I hire someone to film with me for an hour or two in a day. And it usually puts me in a pretty good mood because I like chatting with you guys. I like the stuff I talk about. And so it's pretty good. But I'm not sure all the time. Sometimes I'm not as energized during a stream, and then after like an hour, I'm like, okay, yeah, I gotta end this for sure already. Other times I get carried away and don't even keep track of the time. Another question is, what's my favorite things to teach or talk about when it comes to math? I really like patterns with numbers, are very fun to me because I think they underlie a lot of stuff. And although it's not all of what makes up math, if you learn a pattern about integers or rational numbers or things like that, it can give you cool big clues. So certain things that are important about numbers are like prime numbers, or the opposite of that, super composite numbers, or numbers that have interesting particular traits or lie in particular sequences. So I like when you find something new about numbers that surprises you, that's like, this number does a weird thing. Or here's a trait about numbers that some numbers follow, but there's some surprise in the mix, like that the numbers are rarer than you'd expect, or that they're clumped in a weird way. And I also like when the surprise can be a connection between one fact and a different sort of field or different sort of fact. Like if you say, well, the square numbers are the sum of all the first n odd numbers makes a square number. Well, there's a lot of ways you could visualize that. And you could make it algebraically, you could make it geometrically. So I really like drawing a new connection to a way of saying, hey, this topic was that in disguise. And so there's a lot of things in that I like, but I like when you come across those surprises especially. And the field of math that I've been most focused on this year is definitely the one called number theory. There have been a variety of things I've been interested in the past, but the one this year was mostly focused on number theory. Probably will be a pretty heavy focus next year too, because number theory relates to like which traits certain integers can have, which solutions have integer solutions for which equations, and things like that. And secretly has a lot of magic and is one of those fields that has really simple questions that are really complicated to solve the answer of. And that's another thing I really like, when there's an open question in math about something that is easy enough to phrase in one sentence but is unsolved. And some of those have been solved not that long ago or a while ago or various points in history. So it's not that they're unsolvable, even when it's like a really simple question we've never cracked. Some of them just, we haven't hit the right method yet. So we got someone who's saying the law causes a lot of issues in the comments. I agree that I'm not a big fan of all laws in general. Of course, to my combo lords, I'll recommend try and follow laws when possible. You don't want to get in trouble. And a lot of the laws are moral as well, but some laws are not necessarily, so laws could use adjusting. Laws are not perfect in our societies. And so, in combo class, we definitely hold morality higher than the law. The law can be something to be very important. I'm never going to recommend that any of you break a law, but morality is more important than the law, and they don't always line up. So it's more important to have morals than to know how to follow laws. And secondarily, it's good to be good at playing the game enough to know how to follow the right laws or follow all the laws. But, combo lordness and the combo class and stuff, sometimes I say only break one rule at a time in my classroom. And although I'm not recommending this, I will say that I did relate to the expression being phrased similarly as legally you also sometimes only want to break one law at a time. So sometimes you just got to be careful at what games you play. However, I'm not recommending to break any laws, but I am saying I relate to the idea that laws could change a lot and that they are not the highest stake for how a human should act. Morals are more important. And do I like geometry? And someone's saying law equals morals, which I don't think so. For example, you could have, in a very cartoonish example, like you could have it be, illegal to grow a certain type of berry, but maybe it's not immoral to grow the berry. Maybe the only reason you want to do it is to comply and not get arrested. Maybe, it might not be illegal to pop a little kid's balloon on the street in some society, but it's kind of immoral. So I still think in that society I would more approve of people growing the illegal but safe plant than people popping kids' balloons when it was not illegal. Morals, of course, are not a fixed singular thing either. So they evolve what makes sense over time. So like a moral can't just be a sentence, because a moral is going to relate to, in the current world you live with, what is right to do. And so that's going to evolve. So, for example, the way you talk, you have to talk in ways that are respectful to people, and that evolves over time, what that means. So it's hard to put down in a sentence what a moral would be, but, try and be a good person, try and help more than you hurt, try and bring things to the world, try and be giving and share, try and respect other people's opinions, and then you're probably on the right track. And thank you to whoever just sent a thanks, just wanting to say their appreciation about intellectual passions. I am very passionate about a lot of stuff, not just numbers. So, that'll come up more over time. At first, I didn't feel like I had the right to rant about my opinions because I didn't think anyone would care about them. But now that we have enough combo lords who I have tricked in with my math and science, we can also sometimes think about what philosophy means as well. Someone's asking about additive combinatorics. Cool field. We may look at that in a bit. And yeah, a lot of thoughts about what this means. Someone asked how old I am. I'm 29. And someone asked what non-math related topics I like. Very much like nature. So I'm a big fan of plants and animals. And just like taking walks or hikes in nature where you explore and see new natural phenomena, like rivers. Every river looks different than each other, and they all look different than themselves did a minute ago. Rivers are always evolving. Or seeing, what plants grow, seeing what animals are around. So I'm a big fan of nature. I enjoy reading a lot, so reading can be good, digesting. I used to be a huge reader of fiction. I haven't been doing that as much while I've been reading all this math stuff, but can be cool. I enjoy just joking around with my friends, being silly with friends. That's not really a hobby. That's something that I think is just refreshing for people to do as animals. I enjoy music. I make a lot of music. Hip-hop music, sometimes rock music, sometimes classical music, various stuff I like to write. Let's see what else I enjoy. a lot of it can sound mathematical. Like I like designing games or designing things like that, but those have a mathematical nature. I really like writing, so I write a lot, which could be mathematical stuff, could be just brainstorms for combo class, could be fiction books that I do hope to publish someday. So writing is a big one. And let's see. I like a lot of stuff. It's almost easier to name the stuff I'm not interested in. But I don't know. Yeah, you can always throw a random hobby my way and I'll tell you my opinion on it. Maybe someday we'll do a tier list of hobbies. But yeah, some of my main things that I like to incorporate in my life for sure are nature, laughter, writing and reading, and numbers, and although this is similar to nature, plants and animals. I also can enjoy cooking, can be nice. I like, putting together different ingredients. I like it more than I like eating it almost, is just like the concept of creating a cool bite of something or of like cooking an interesting recipe. Someone says, solve this. My religion says I don't have to obey your laws. So I think that as a society, we do have to stick with laws. Laws that we have for public safety need to be above religion. So even if a religion says you can do something illegal, it still has to be illegal. I think that religions should be separated more from legal and schooling stuff. I think there should be more of a separation, as they say, of church and state. So although I say morals are more important, I still think that like the system has to be for a police person to arrest someone who breaks the law. We should change some laws to be better laws, but the system still has to be that you get arrested if you break the law, although the laws should be better. And religion shouldn't be able to trump that and change that. But what I mean about morals is just that combo class is a little chaotic. I can't say all this stuff directly on a stream. I don't want to get YouTube mad at me, but I've broken plenty of laws in my day. I'm not going to recommend it to you guys. I'm a wholesome, moral channel. But all I'm saying is that I'm a moral person more than I'm like a strict law follower. I do things that I think help the world. However, I believe that if I were to break a law, in the system, I should be arrested and religion should not be the excuse. However, some laws should be different. I don't teach in a brick and mortar school. I used to actually teach in a music shop that was a brick and mortar music shop. And then I ended up switching to digital teaching, partially because when COVID hit and partially because I had to get 2 surgeries and a lot of crazy stuff, and I had to get my hips operated on and all this stuff. And so I taught in a music shop, one-on-one private lessons there a while. And then I switched to digital, and now I run my own lessons. So I just teach digitally right now. But I haven't taught in a school-type school. So, let's see. And yep, some people are saying they can be good in different ways. Someone wants to know my inspiration for designing my classroom as it is. So, there's a lot of symbols that I like to put in my classroom. And those symbols include dice, clocks, whiteboards, nature type things, which includes kind of like the earth is like the dirt and the staghorn fern and plant like things. I like including I intentionally included 3 of the 4 classic elements. I was like, I'm going to do this in the dirt, I'm going to do this in the fresh air, and I'm going to sometimes have things on fire. And I was like, water is the 4th classic element. Maybe I should put water in as a theme. And then I was like, no, probably in a later grade, I'll decide to put water as a theme. We'll have floods and stuff like that. And then the rain decided for me, nope, it's going to be grade -1 gets that theme. So the rain decided for us that all 4 elements got represented. So the 4 elements of those classic 4 elements are sort of at a core of what we've been working with, are dirt, air, fire, and water. As far as the clocks and dice, I mean, the whiteboards are kind of self-explanatory. I want to teach outdoors. Whiteboards are cool. I like them more than chalkboards. The clocks and dice are on a list of symbols that I love, that I've written down, and there were other symbols that will recur in future grades along with the clocks and dice accumulating. And these are symbols that I've put in a lot of my fiction books too, because I think they're very symbolic. What a die can mean, and what a clock can mean. Representations of time, representations of chance. And so they're very symbolic items I've used in a lot of books. And then as I started studying math, I learned more and more math things about them. Where like clocks, I was like, okay, they got highly composite numbers on them. Okay, they relate to modular arithmetic. Okay, clocks also relate to ways of describing all these other patterns about prime numbers and stuff. And so I kept learning stuff that could be described clock-like. And there's even other episodes I'll make about clocks that are whole other things, like how clocks are like donuts. And so I realized that the clocks and the dice are like, okay, so they are different platonic solid shapes. What shapes can things be? They're probabilities. You can rewrite the numbers on them to have weird paradoxical phenomena we're going to go into soon on my blank dice when I make my own homemade dice. And so I found all this different math stuff about them, and they were very symbolic to me already. So I decided we are going to have a bunch of them. Now, in combo theory, which I will explain more about in the future, we like to combo different things together. However, sometimes we also need what's called contrast theory. And that can rely on having, instead of a combo of 5 million different things where you don't even notice any of them, having a combo of like 5 or 10 different things that you each have quite strongly emphasized. And so within the chaos of the classroom, which I knew would build, I decided let's have a cartoonish degree of emphasis on a few of the symbols. And that ended up including clocks and dice. Then if you want to know why I got so enwrapped in the clock quest part of it, watch the episode on my main channel called Why I Have Dozens of Clocks, because there's a little funny story as to a promise I got enwrapped in and so on that eventually has me on my clock quest to accumulate hundreds of clocks, which I'm still on. I promised at one point 1,000 dice, and I've gotten more than that. So there are more than 1,000 dice in the classroom. We can chill out on buying dice for a month or two, but we need to get back on our clock game. We've been destroying as many as we've accumulated. Now, I may at some point in a month or two start, maybe even for February, start a P.O. box for people to mail broken clocks. So leave a comment if anyone ever sees this, if you would mail a broken clock to a P.O. box. Or it doesn't have to be broken, but if it's broken, then you don't even need it, so why not send it to me? So I may need to accumulate my Combo Lord's old broken clock so we can have grade -2 have an absurd amount. So, and someone mentioning topology, I'm not sure exactly which one you referred to, but if you meant when I was referring to it being like a donut, I do mean in a way a topological donut, a torus. Someone saying generic gaming devices like cards, dice, and dominoes are very deep culturally and mathematically. I agree. Those are all symbols that may occur. One symbol we may see a lot of in future grades are game pieces. For example, chess pieces or checkerboard grounds. And game pieces are very symbolic. Cards, too. I did think about scattering an absurd amount of cards, and I bought a bunch of cheap cards. I have a ton of decks. So at some point, those might end up scattered, too. And they are very deep and very mathematical, all those simple game pieces. Dominoes, actually, are just the first level of an even cooler one, though. Let me see if I have any here. I think I have mine outside, unfortunately. But these things called... Oh, here I have an example of a different one. This was for a video I filmed a while ago. So these are cutouts of tetrominoes, which, think about the word root. Domino, D-O, often means two. Domino just means like two minnow. It has two cells, and there's only one way to connect two squares side by side. But with four squares, we have all the tetromino options, including the other ones. And it turns out the pentominoes, the ones with five cells, are super fun to put together in puzzle shapes. They make an absurd amount of rectangles because there's 12 of them, and that are like possible to connect in that way. So they give you all the one of each, and they have 5 cells each, and 5 times 12, 60. And with the divisibility, it actually does work that you can make so many different rectangles perfectly fit from them. So that's like the funnest puzzle piece like thing. Let me show you on the screen here real quick. Our pentominoes. So these are our pentominoes. Some of them, like this is showing the options if flipping counted as a different one, but in the puzzle piece ones, you count these as the same piece, and so there's 12. They can make a lot of rectangles like that. Don't look at it. It will be spoilers. It's more fun to do it yourself. Pentominoes, you can see here, are a polyomino, is the name for the generalized type. And polyominoes are super interesting to me, how many of different types of polyominoes exist, which ones can make rectangles or not. So we're for sure going to play with those a bunch sometime, and those will maybe be one of the recurring things that gets scattered a lot too. I've already lost my original set of pentominoes somewhere in there. So I do think I'm going to end the stream soon. I appreciate you all for joining. You're all super awesome. Make sure that all of you have seen the main channel episode that's in the description here. And also that you've seen the new shorts I've been dropping on this channel. They're pretty casual, but I filmed a bunch of shorts the other day, and we still got a few more to come. So, some casual, fun shorts in the mix of our streams and stuff. I'm still not positive what my streaming schedule is going to look like for this next week, but I will stream again very soon. Small chance it could be later tonight. To whoever said they just joined, you can always rewatch the streams. I try and make them fun for that too. And I may even stream again tonight or tomorrow, because a fun idea I thought I might want to try, and this is very different, but to everyone who keeps asking about my music and stuff, I thought it would be fun to stream making a beat on GarageBand, which is one of the simpler beat programming softwares. Could be kind of fun to watch me make a beat from scratch. You guys could maybe even give input. You could help me pick the instrument sounds or whatever, pick which key we're in, and I'll make a beat from scratch. And that could be a fun stream. We also could do a little more of a reading club stream where we take a peek at some more of these books I've been going through, because we got just stacks and stacks of books. A lot of these I got to read through. So to whoever who's recommending books to me, I still have some to finish. But in any case, I love you all. I'll catch you again whenever I do those other fun streams. Another one to look out for, apart from the me programming stuff on there, is we're going to do a stream where I go through a tier list of classroom supplies, while we'll also look at how trashed my classroom got and which things got destroyed by the rain. So our tier list will help us realize which things we still need, because any S tier or A tier classroom supply that is destroyed, I'll put on a list to restock for grade -2. Or some of them I may not have yet. So it'll help us remind what classroom supplies I'll need to buy for grade -2. Do I need more rulers, calculators, what? And those are some fun streams to look out for, either tonight or in the next couple days, of ranking some classroom supplies, and a different one where I'll make a beat. So you all are super awesome. Love you all so much. Let's switch to 13 months, or if we can go for 6-day weeks, let's switch to that other proposal. And until then, I will, not until then. I will, see you before then. So until next stream, not until we switch to 6-day weeks, I hope you have a marvelous time. Stay excited about all this learning and lifing that we're doing. And to those of you having a hard day, hope things that go easier. We will continue to find ways to be happy and excited through the hard times throughout our future streams and episodes. And that's where I'm going to cut it off now. Love you all so much, and make sure if you didn't catch the beginning bits to watch the beginning of this stream and learn a little bit about some modular arithmetic. Alright, bye folks.